So, so today I'm going to talk to you about our project, decision-making with naturalistic options. And so this is a joint project between our lab, Computational Principles of Intelligence at Tübingen, and Christian Doller's group at Leipzig, Max Planck Institute. So to start off with a real-life example, imagine the following scenario where, say, after your talk at COGSA, you want to go to the supermarket and get yourself some cookies as a treat. But when you go to the supermarket, you realize that your favorite cookies have run out. But this shouldn't be a problem for you, because most likely you can successfully generalize what you like about these cookies to make another good purchasing decision. So, for example, you know that you like sweet cookies but not so sweet, and you maybe also want to get something not so expensive. And depending on these parameters, you should be able to make another good purchasing decision. And how we study decision making in the lab settings could be as follows. For example, you see the two stimuli that are on my screen. We might present participants with these two stimuli, ask them to pick one or the other, and once they make their decisions, we might, for example, show them the rewards or the values associated with these options, right? And in this example, you can see that the features of these stimuli are clearly separable to the eye, and this feature space is very low dimensional. So, right, you can see that we're dealing with one horizontal and one vertical line. And from a single trial, it shouldn't be too hard to infer that a longer horizontal line means a more rewarding outcome. If you, however, consider the scenario on the right, say you're presented with the image of a cat and the image of a fork and get some points associated with that. Here in this example, the features are not clearly separable to the eye, and the feature space is likely very high dimensional, and it may not even be clear to you what a given feature is, right? And so after seeing this one trial, a clear reward structure may not emerge for you immediately, and you might have a lot of different ideas about what might be rewarding and what may not be rewarding. So to set up our study, we have three goals, and our first goal was to test if people can generalize successfully about rewards in naturalistic high-dimensional feature spaces. The second one was to test whether insights from previous studies with artificial stimuli, like the ones that I showed to you, transfer to more naturalistic feature spaces. And lastly, we also wanted to investigate what kind of representations people might be using when they face naturalistic reward-guided decision tasks. Okay, so before we talk about the trial structure, perhaps I should introduce the stimuli that we use. So we use this database called Things Database, curated by Martin Hebert and colleagues, which is a rich database of naturalistic real-life objects, right? And you see some examples here, like a laptop, noodle, peacock, and a microscope. And what Martin Hebert and colleagues also did was they showed that these images can be described 49 latent features, which they extracted through a combination of similarity judgments made by humans and computational modeling. So, for example, for the laptop, you see that its technology feature is quite high, whereas for the noodles, its food-related feature is an important characteristic. And what we did in our task was we told participants that they will be shown pairs of images, and each picture is associated with a specific number of points in a non-random way. And we asked them to choose the object that gives more points to them. And once they make their choices, they are shown the points associated with both images. And how we decided on the reward structure was that we took the values of one of these latent dimensions. Martin Hebert and colleagues extracted the latent dimension that explained the most variance in the data set, which was how artificial, hard, or metallic an object was. And we scaled these values between 0 and 100. And we had 150 trials in total, and we ran the study on 25 participants, and we randomized the order of trials across participants. So to give a better intuition of the reward structure, here you see the less rewarding options on your left and the more rewarding options on your right. So for example, the tool on the very right is very rewarding because it's very metallic. So are drums. for example, but the raspberries that on the very left, they're not metallic, they're not artificial, so that this image wouldn't give a participant a lot of points. And now onto the results. Our first finding was that people can indeed generalize successfully about rewards. So in the first plot, the one on the very left, you see that the mean regret of participants goes down over trials, so they can accumulate better points as they progress through the task, which indicates learning. In the second plot, you see the probability of choosing the left image as a function of the reward differences between the left and the right image. And here you see a nice sigmoid shape, which is commonly seen in decision-making tasks, reward-guided tasks, where when participants understand the underlying reward structure. And on the third image, the third plot, you see the results of our logistic regression model, in which we tried to predict participant choice using reward differences and the trial number. And you see that the reward difference is a significant predictor of participant choice, and importantly, that there's an interaction between reward difference and the trial number. That is, as participants go through the trials, the reward difference between the options seem to be a better predictor of participant choice, again indicating learning. And in the fourth plot, you see 49 the results from 49 different logistic regression models, where we try to predict participant choice using the values in a given latent dimension. And here you see that when we try to predict participant choice using the first latent dimension, which is how metallic objects are, that one seems to predict the participant's behavior the best compared to the other latent dimensions, again indicating that participants seem to have a good grasp of the underlying reward structure. Now onto the modeling. So to get a better understanding of the processes behind participants' decisions, we took the following modeling approach. So we took our learning models and we trained them on all 49 latent features to predict the rewards associated with these latent features. And we would train the models until trial N, and for the trial after this one, we would get reward estimates from these models to predict participant choice. And we tested 4 models, the first one being a regression, which is a model that learns linear weights over these features. Our second model was a non-parametric Bayesian model called Gaussian process regression, which makes predictions based on the similarities between its training points. And our last 2 models were heuristics models, where the single Q model makes rewards estimates based on the best predictive feature and one feature only. And equal weighting is also a type of linear regression model that just learns a single weight for all the latent features. And what we found was that here you see a model comparison result, and we found that the linear regression model was the most prevalent model in our participant population, and that the human behavior in our task was best explained by this model. And lastly, we also need to consider the possibility that the humans may not be using the latent features on which the task was designed, but that they might be using other representations, right? And obviously, the feature space that you have here is infinitely large, but one hypothesis we thought could be interesting was, can we train our learning models with pixel-based representations that we get from pre-trained convolutional neural networks? And if we train our learning models with these pixel-based representations, would these provide to be better predictive of human behavior in our task? So on the plot on the left, you see that this is not the case. So the learning models that were trained with the pixel-based representations do not have as high of a predictive accuracy as the models that were trained with the original latent features. But another interesting finding that we have here is what I showed you on the right, which is, again, we train a logistic regression model trying to predict participant choice. And here we used two different regressors. The first one being the value estimates, the reward estimates that we get from the linear regression model that was trained with the original latent features. And for this regressor, you see that our beta value is quite high. But also interestingly, when we also add as a regressor the value estimates that we get from a linear regression model that was trained with the pixel-based representation, this predictor also seems to be a significant one, indicating that these pixel-based representations may capture a part of how people represent the stimuli in our task that is not captured by the original latent features. So to sum up, we show that participants can learn to generalize over rewards in a naturalistic high-dimensional feature space. Since no stimulus was repeated twice, to perform better in this task over trials, they had to learn something about underlying structure, which is an indication of generalization in this case. And we show that people use a linear strategy, like previous studies have shown that on reward-guided decision-making that have used low-dimensional and artificial stimuli. And lastly, the stimuli representations that we get from convolutional neural networks capture a part of the representational space people use while they deal with these naturalistic images in a reward-guided task. And yeah, thank you all for listening, and thanks to all my supervisors and collaborators on this project. Thanks.
Thanks for the great talk, Ken. So we have some time for questions, either in person or virtually. If you want to ask an in-person question, just go ahead and line up behind the microphone in the middle. And there's someone there, so just go ahead.
Cool, very nice talk. So in this task, it seemed like people had to make decisions based off of something physical about the stimuli, the metallic nature, artificial nature, etc. What if instead the representation was based on something more abstract, like a goal? Like, could you use it to build a boat, or could you use it to create a fire? How might your conclusions change?
Yeah, thank you. I think that's an interesting question. So we're just here using, as you said, like one of these 49 latent features. And if you look at the original paper by Martin and colleagues, some of these other latent features are similar to what you described. So for example, whether something is construction related or so. The answer is we don't know, because we haven't tested it yet. But I would imagine still that people may be able to pick up on more abstract features as well. But I suppose that's an empirical question that needs to be tested.
There's an online question. It's related to this first question that you have here. If a hypothesis is that alternative representations are being used to learn reward points, why use pixel values as the alternative to your existing feature space, as opposed to some other method of deriving features?
Yeah, so is the question on why do we use pixel-based representations as an alternative feature space and not some other feature space?
Mm-hmm.
Yeah, so I mean, I think that's a fair question. Again, like as I said, the possible future spaces that people might use is practically infinitely large, right? And the reason why we picked convolutional neural network representations is because like over the last decade or so, people have been showing that these seem to be good models of the ventral visual stream for object recognition, and we were wondering whether these representations that are used for object recognition may also translate into like a reward guided task. But like surely, like you could, I think, come up with like other interesting feature spaces to test as well.
And we have another in-person question.
Hi, great talk. Thank you. How do you see value-based decision-making as being related to categorization? Have you imagined that different sorts of valuations might influence categorization?
How does value-based decision-making relate to categorization? This is I suppose it's like something that we've thought about a little bit about this task. So here in this case, for example, our reward structure was based on whether an object is like to what extent an object is metallic, right? And like one of the things that we were thinking about was also, or maybe people just perceive some objects as metallic and artificial, and other objects as not metallic and artificial. So I suppose you could design a task where there's like a correct or a wrong answer in a classification task, where you have a cutoff point for how metallic something is. And I would imagine again, people would be able to solve the underlying structure. So I guess like the answer is like my answer is I would imagine that if people can figure out this structure in a reward guided task, they also should be able to in a categorization task, I think.
That's really interesting. Thank you.
Yeah, thanks.
Are there any final online questions? Okay, if not, let's thank Can for a great talk again.
Okay, thanks very much.